Statistics class. Today we will quickly brush up the theory of probability chapter. So what is probability? I think many of you have done this. Probability is something related to chance of occurrence of events. When we are not 100% sure that an event will occur with certainty, then we say that the event may occur or may not occur. That is, we are in a probabilistic situation. For example, suppose when we see clouds in the sky, we can be probable that it may rain, but we cannot be certain that it will rain today. Dealing with this chapter, we will also study some kind of some basic terminologies. The first one is a random experiment. So what do you mean by random experiment? If in each trial of an experiment conducted under identical conditions, the outcome is not unique but may be any of the possible outcomes, then such an experiment is called a random experiment. Suppose in throwing of a die, the possible outcomes are 1, 2, 3, 4, 5, 6. When we perform our experiment, suppose when we throw a die, it is called an experiment, okay? Then the possible outcomes which may occur are 1, 2, 3, 4, 5 and 6. Out of these, we cannot be sure which of them will occur. Either 1 will occur, 2 will occur or 6 will occur. So, when any experiment has an associated probability with it, we call it a random experiment. Next, we move on to another definition, that is trial and event. Trial is a performance of an experiment and event is the outcome of a trial. Both are not same. Trial, when we perform it, suppose when we throw a die, it is called a trial. But what are the outcomes? 1, 2, 3, 4, 5, 6 are known as the events. Then we have the exhaustive event and favorable event. Exhaustive event, the total number of events that satisfies a random experiment. Suppose we consider an event of the number of possible outcomes in throwing a die. The total number of possible outcomes will be 1 to 6. But in favorable cases, if we say the possibility of an even number, while throwing a die, the total number of even numbers will be 2, 4 and 6. So here it will be 2, 4, 6. And probability, as you know, is favorable number of cases divided by total number of cases. That is, here equals to 3, n of a, it is 3 and here it is 6. So we have 3 by 6 equals to 1 by 2. That is, when we throw a die, the favorable number of even numbers, the probability of getting even numbers will be 1 by 2. We will deal with certain basic definitions. I will give you some flashcards regarding it. Then we have 3 definitions of probability. The first is the priori definition, which was given by Laplace and Bernoulli. Let us check what the mathematical definition or the classical definition has to say. If for a random experiment there are n mutually exclusive, exhaustive and equally likely outcomes and m of them are favorable to the happening of an event A, then the probability of happening of the event A is given by probability of A is equal to m by n, where is the m is number of favorable cases, favorable outcomes, and n is total number of outcomes. this has certain limitations because we assume that the outcomes are mutually exclusive, exhaustive, and equally likely. Mutually exclusive means the happening of one does not prevent the happening of other event. Exhaustive means all the outcomes, all possible outcomes should occur when throwing a die. Suppose if in a die we know that there are 6 faces, 1 to 6, and if suppose 2 or 3 does not occur, then that die is not exhaustive. That die, two of the remaining outcomes will not be shown through that die. And equally likely. What is equally likely? Equally likely means each of them has a probability of 1 by 6 associated with it. There is no chance that one will occur more than 2 whenever we throw a die. Each of them have an equal chance of occurring. Then we have the statistical or empirical definition of probability. It was given by von Mises in 1920. The statistical definition says that the probability of the occurrence of an event is the ratio of the number of times the event occurs to the number of times the experiment is conducted, provided the experiment is conducted an infinitely large number of times. Symbolically, it shall be, if A is the event to be occurred, the probability will be limit n tends to infinity n by n. That is, even the experiment is conducted for an infinitely large number of times, it will be equivalent to the probability of happening of the event. Suppose in throwing a coin, the probability of a head appearing is 1 by 2. Even in the case of tail also it is 1 by 2. However, if we conduct the same experiment of throwing a coin 100,000 times, and we see that head occurs for 512, 51, 502, 498. After conducting the experiment, that is when a coin is thrown for 1,000 times, we see that in those 1,000 throws, head has occurred for 512 times, 502 times, and 498 times. In that cases, probability of head will be 512 by 1000, 502 by 1000, 498 by 1000. In all these cases, the probability is equivalent to 1 by 2. Not nearly, it will be something 0.5, that is, shall be something near about to 0.5 something. Here also it will be the same cases, and here it will be near about 0.49, equivalent to 5, which is the probability of occurring of a head when one coin is tossed. That is, when an event is when an experiment is performed for infinitely large number of times, it will tend to the basic probability which it inherits. That is the statistical definition of probability. The statistical definition is not mathematical in nature, and it requires the experiment to be conducted very large number of times under the same conditions, which is not possible in many situations. For example, you have started to toss one coin for 1,000 times from this time onwards, but you may not be able to conduct the same experiment continue the experiment for another hour, because you may have other classes or household work. So under same identical conditions, you may not be able to perform the experiment. So this is a drawback of the statistical definition. Now we move on to the axiomatic definition of probability. 1933, Kolmogorov gave this definition which removes the drawback of both classical and statistical definition. The modern approach to probability is axiomatic and is based on the set theory. So, let S be the set of all outcomes of an experiment and A be any event, then probability of A will be called probability of the event A if it satisfies the following three axioms. That is, axiomatic definition is based on three axioms that needs to be satisfied whenever we are dealing to check the probability of an event. Probability always lies between 0 and 1. When will probability be 0? When it is an impossible event. Like, what is the probability of getting a 7 in throwing a die? We have only 6 faces from 1 to 6. So, probability of getting a 7 in throwing a die is 0. So, it is an impossible event. Another example. Okay, now we will say, when will the probability of an event A be equal to 1? It will be equal to 1 when it is a certain event. You are certain that this event is going to occur. Suppose in a leap year, we are talking about a leap year, and we say what is the probability of a February month having 29 days. So in a leap year we have 29 days for the February month. So it is a certain event. That probability is 1. That month in that leap year will have 29 days. So probability has to lie between 0 and 1. This is the first axiom. The second is probability of S equals to 1. That is, S is set of all our possible outcomes. It may have A1, A2, up to AN, which implies summation of all these AIs are equals to 1 to N equals to 1. Okay. Probability of all possible outcomes have to be 1. Suppose in tossing a coin, probability of getting a head is 1 by 2. Probability of getting a tail is 1 by 2. Probability of S, that is set of all outcomes, is what? Probability of H plus probability of tail, which is equals to 1. Now we will deal with the third axiom. Probability of A1 union A2 union up to AN is equal to probability of A1 plus of probability of A2 plus of probability of AN, where A1, A2, AN are mutually exclusive. What is mutually exclusive? Probability of A1 intersection A2 will be equal to 5. That is, both are disjoint. This is the third axiom that must be satisfied. When we deal with the axiomatic definition of probability, we have to study certain algebra of events. Algebra of events, I will give you one flashcard regarding it. You have to note it down and learn them by heart. Also, by drawing set diagrams, you need to relate to it. I have also shown how which of them satisfies which law. Then we will deal with the additional rule of probability. according to the additional theorem, A1 and A2 are mutually exclusive events, then probability of A1 union A2 is equal to probability of A1 plus A2. When they are not necessarily mutually exclusive, if A and B are two events not necessarily mutually exclusive, then probability of A union probability of B union B will be plus probability of B minus probability of A intersection. These are the basic additional rules. We have another rule regarding three events which I have shown you in your flashcard. Then we will move on to the conditional probability. Suppose we are interested in a pair of events A and B, and we know that event B has already occurred previously. Now we want to know the probability of occurrence of the event A given B has already occurred. Conditional probability. Suppose we are interested in two events A and B, where we know that probability then event B has already occurred. Then the probability of A given that on the condition that B has previously occurred is denoted by this, that is probability of A intersection B divided by probability B, provided probability of B is greater than 0. In the same case, probability of B event B given the condition that the event A has previously occurred is equal to probability of A intersection B divided by probability of A, given that probability of A is greater than 0. In both these cases, we assume the denominator to be greater than 0 because it's obvious when we know that when the denominator is 0, the value will be infinite. So anything divided by 0 is infinite. And when it is in the numerator, it is 0. We have the basic maths concept here. Now we will deal with the multiplicative law of probability or theorem of compound probability. Some of these theorems need extensive proof. So I will give the proofs in your notes. And also in the flashcards, I have given the whatever is written in the board. I have sent you flashcards. It is not possible to extensively show in the small blackboard all the theorems and proofs. When the normal classes resumes, we will do all the proofs one by one along with certain sums which are very long. The short sums I will be showing you in this board itself, but those sums that requires the utilization of theorems, we will do it in the class. Now we are having the theorem of compound probabilities. The definition says that the simultaneous occurrence of two events A and B is the product of the conditional probability of one and the unconditional probability of the other. That is, probability of A intersection B intersection B means both A and B occurs together, is the product of the conditional. First we write unconditional, then we write the conditional. Unconditional probability of A, suppose given that probability of B given A has already occurred. Okay. Whatever we write in the unconditional section, that will be the denominator of the second one. Same case, probability of A given B is equal to probability of B into probability of A given B has already occurred. Now, we know that when A and B are independent events, then A intersection B is equal to into probability of B. So, in case of the theorem of compound probability, probability of A intersection B will be equal to A into B. That is, probability of B given A will be probability of B given that A is already occurred. Since A and B are independent, B will not be dependent on whether A has occurred or not. So it shall be only dependent on probability of B. This method does not matter because A and B are independent. Similar, when probability of A given B is to be found, we have probability of A, because it does not matter whether given that the conditional probability here is 0, means 5, not 5, it is independent. So these are the basic things which we will study in this chapter. We are to do certain theorems of the conditional, the compound and the additive theorem of probability. We will look into some proofs. I will give you notes, and if you do not understand, you can always contact me. These are the basic things which we will study in this chapter. Next, we will do some sums and theorems on this chapter itself. It will take another 1 or 2 classes. Thank you.